All right, folks, back here with another video studying application of derivatives and looking at functional analysis with this derivative operator. And again, we're going back to analyzing slope of tangent lines and using that information to help us draw conclusions about the behavior of a function. All right. And our last video, if you've checked that out, we talked about critical points. And what's interesting about critical points is many of the critical points we encounter end up becoming boundaries between our intervals where we're increasing and decreasing in value. All right. Let me bring my notes into play here. All right. I open by saying that, right? Between many critical points, right? F of x is either increasing or decreasing, or we could have the case for remaining constant in value, an interval where the slope is constantly zero, but that would be only seen mainly in constant functions. But critical points within the domain of y equals f of x are potential boundaries between our intervals of increasing, decreasing, and that potential constant behavior. Not all critical points are boundaries between intervals of increasing and decreasing, particularly when we think about inflection points. Right? Inflection points, when we think about that cube root function, it was constantly increasing. And it did have a critical point at 0, but that was because it was an inflection point. And those are going to be situations where that inflection point doesn't really play a role of a boundary. So they're not all boundaries, but there is good potential for them to be a boundary. All right. Let's look at some examples. I think I opened with some. Consider again the two functions we've already kind of discussed here. We looked at this polynomial already, x cubed minus 3x squared minus 24x plus 27 plus 7 when we were back looking at critical points. And we found that the critical points of this function were negative 2 and 4. And those were negative 2 and 4 in a domain from negative to positive infinity for this function. So if we think about these critical points in this domain, they do subdivide the domain into three equal portions, right? You have from negative infinity to negative 2, from negative 2 to 4, and from 4 to infinity, where what these become are our potential intervals for increasing, decreasing, and constant behavior. What we need to do is look at the behavior of the function over those intervals. And since we already have the graph, right, we should be able to go back and see that we were increasing, right? We were increasing from negative infinity to, why do I have, that should say negative 2. Let's fix that. That's why I'm going through these, just to double check them, right? That should say negative 2. Right? And from 4 to infinity, we are increasing. We can see that we're increasing in here. From negative infinity down here all the way up to negative 2 along my x-axis. From all the way down here at negative infinity up to negative 2, I am increasing up this portion of the function. And then I begin decreasing at negative 2 to 4. From negative 2 to 4 along the x-axis, I am decreasing, moving down. And then at 4, starting at 4 out to positive infinity, I am back increasing up the right side of this function, all right, from 4 to infinity. So I am increasing on those intervals from negative infinity to 2 and from 4 to infinity, and decreasing from negative 2 to 4. Those intervals that formed in our domain, right, that were bounded by our critical points at negative 2 and 4. Many of our critical points play the boundaries in our intervals of increasing and decreasing. All right? we see that in this case, and we see it in the following case. If you go back and reconsider that rational function in our last example, right? Our critical points were at plus or minus 2, -6, and -2/3. Where this was all within a domain, if we think about F's domain, we were not allowed to be that plus and minus 2. At plus and minus 2, we had critical points that were vertical asymptotes in our graph. Well, those do subdivide our domain, where if we then go back and include the other critical points into that subdivision, our entire domain from -infinity to +infinity can be subdivided into these 5 portions, where over some of these portions we're increasing and over some of these portions we're decreasing in our behavior. If we break those down, what we do see on the graph is that we were increasing. We were increasing from -6 to 2, which is this little interval right down in here. Oh, sorry. From here to here is -6 to 2. That's where we're increasing. And we're also increasing. Now I have something. Yeah, -6. I'm looking at the wrong thing. From -2 to -2/3, this little interval right in here. This is also where we're increasing from -2, starting at the vertical asymptote, to this location on the x-axis, just this little interval right here from -2 to -2/3, we're also increasing. From here to the vertical asymptote, and then from the vertical asymptote to -2/3. We are not increasing at the vertical asymptote, though. So we don't say we're increasing from -6 to -2/3. That vertical asymptote is not in our domain, so we can't include that in an interval of increasing behavior. So that is why we do see that interval from -6 to -2/3 subdivided into 2 portions at that domain concern of -2. Everywhere else, we're decreasing from -infinity to -6 in this portion here. From -2/3 to 2 from this extreme value on down. Right? Or from -2/3 over to this value of 2, we're decreasing. And then from 2, starting at this vertical asymptote out to +infinity, we're decreasing. As we had noted, the critical points subdivide our domain into intervals, into potential intervals of increasing and decreasing behavior. And we see that here in this example. The vertical asymptotes are not in our domain, so those are included in our list of critical points, and they do also play the roles of boundaries. And this entire region from negative to +infinity is subdivided by those vertical asymptotes and those critical points at -6 and -2/3. Right? And those become the boundaries on our intervals of increasing and decreasing. Now, in the last 2 examples, we did have the graph. We are going to want to consider, well, what happens if we don't? Well, if we don't have the graph, then what we have to do is perform a bit of a sign analysis on our slope function, f prime of x. Where f prime of x is greater than 0 is where we're going to be increasing, and where f prime of x is less than 0 is where we're going to be decreasing. And we see that help us define our intervals of increasing and decreasing. All right? For some function y equals f of x, the interval I from a to b is an interval of increasing behavior in f's domain if f prime of x is greater than 0 for all x in I. And similarly, if it's less than 0 for all x in I, it is an interval of decreasing behavior. And with respect to intervals of increasing and decreasing, they are open intervals in that domain. right? We are talking about intervals that are always never including their boundaries in their descriptions. If we're increasing at a boundary, then that is not a boundary of an interval of increasing and decreasing behavior. All right? Take note. So if we look at an example, we could just analyze the sign of the first derivative. And if we consider this quadratic seen here, x squared minus 5x plus 8, if we look at its first derivative, f prime of x is 2x minus 5. And if we solve for the critical point there, setting that equal to 0, that is equal to 5 halves. There are no critical points because it doesn't exist anywhere. It exists everywhere. So the only critical point is at when it equals 0, the first derivative, and that's at 5 halves. So over that domain from negative to positive infinity for this quadratic, right, 5 halves has the potential of subdividing that interval into intervals of a decreasing and increasing behavior. Now, if we take note, quadratics are parabolic behaviors. They are either opening up where they have a portion that's decreasing and a portion then that's increasing, and or vice versa, right? They open down. We could analyze a bit of sign to help us determine this. If we just note for values less than 5 halves, right? If we start to look at values like 0 is less than 5 halves, plugging 0 into this function is going to give me positive 8. So if 0 is in this interval, that means I must be an interval there where I am increasing in behavior. Right? And likewise, if I look at a number that's in this interval, 5 halves is at 2.5. So if I pick a number like 3 and I substitute it in here, I will have 9. Let's be careful with this. Sorry, 5 halves is, yeah, it's 2.5. So if I put 3 in there, I'll have 9 minus 15. Now let me back up a moment. Where am I confusing? Oh, you know how I'm confusing this? I'm plugging it into the wrong function. My apologies. We are evaluating 0 in this interval in this function, not our original function. There's my confusion. When we evaluate 0 inside here, right, 0 is a value between negative infinity and 5 halves. And when I substitute in 0 here, I do get negative 5. So that is where it's less than 0. That must be where I'm decreasing. And if I pick a number like 3 and I substitute 3 into this value for f prime of x, 3 times 2 is 6 minus 5 is positive 1. So that is greater than 0 in that interval. So that must be where I'm increasing. So I can analyze the sign of my function's behavior over those two intervals, and without the graph, be able to determine where I'm increasing and decreasing in behavior. Right? If we consider doing this for a little bit more complex scenario, here is this polynomial function, negative 2/3 x cubed minus 3/2 x squared plus 35x plus 10. If we consider its first derivative, it should be quadratic, where I do believe I set up this quadratic so that it factors nicely, and it does factor. It factors into negative the quantity 2x minus 7 times the quantity x plus 5, which means we have zeros or critical points from this first factor that are at 3/2, 7/2, and from the second factor at negative 5. So those are going to subdivide my domain from negative to positive infinity into what is that? 3 separate intervals. From negative infinity to negative 5, from negative 5 to 7 halves, and from 7 halves to positive infinity. And that's what we see here. We can then test numbers in that interval in each of our, well, within f prime of x. So if I pick a number like negative 6 and I substitute it in here, notice the sign. It'll be negative times, this is going to be a negative. 2 times a negative, 6 is a negative, minus 7 is also a negative. So a negative times a negative is going to be negative, and then times negative 6 plus 5, that's also going to be another negative. That's going to be negative 1. So a negative times a negative times a negative is a negative value. So since negative 6 makes f prime of x negative in this interval, we can say in this interval we must be decreasing. All right? Whereas if I use 0 in here, because 0 is between negative 5 and 7 halves, notice this will be negative and this will be positive, which is a negative in product. But then times this negative will become positive. So if 0 produces a positive value for f prime in here, then we must be increasing, and we are. And 7 halves is at 3.5. So if we take a number like 4 and substitute it in here, notice this will be positive 9. This will be positive 1. So positive 1 times 9 is 9, but then times the negative would revert to negative 9 again. Well, that negative number is less than 0, so the slope would be less than 0 or negative in that interval there, 7 halves to infinity, so we must be decreasing on that interval. And that is exactly what we see happening in the graph of this function. Right? If I evaluate it at some test values, I do think I use negative 6, 0, and positive 3. We can see negative 6 gives us that negative 19. Can I go up a little further here? This just looks funky spaced, but I guess it is what it is. F prime at negative 6 is negative 19, so that's less than 0, so we must be decreasing on that interval from negative infinity to negative 5. If we look at 0, I think that's the next test number I use. Oh, I actually use 4. All right, instead of 0. But 4 works the same. You can see you have a negative times, sorry. That's also where we're decreasing. So that is, again, we see that negative 9. So that gives us another interval of decreasing. And then if we test that 0, I test the 0 last. I don't go from left to right for some reason, but that's fine. We do notice that gives us positive 35. Since f prime at 0 is greater than 0, right? Positive 35, that must be an interval where we're increasing in behavior. So our intervals of increasing and decreasing behavior have us only increasing between negative 5 and 7 halves. And that is what we see here in the graph. Between negative 5 and negative 3 halves, we are strictly increasing. And then we are decreasing starting here at negative infinity up to negative 5. And from 7 halves to infinity, we are still decreasing. And you can see we performed a little bit of an analysis of f prime at the value of 0 and around those critical points that we find at the value of 0. And that will help us break down those intervals where those critical points subdivide our domain into where we might find increasing or decreasing behavior. Very seldomly are we going to encounter the case for constant behavior. All right? So that is intervals of increasing and decreasing, folks. It is going to be the first thing we can use our critical points for. Is they're going to play the role in finding the boundary of these intervals. They were the boundary on the intervals seen here in this graph of the polynomial at the end. They were the boundaries on this quadratic example for the parabola. or it was the boundary. There was only one there. And they played the role in the boundaries in the examples that we've seen previous. They aren't always going to bound every interval of increasing and decreasing behavior, however. Because if we go back and we consider that case of the cube root function, we had a critical point at 0 there, but it's constantly increasing from negative to positive infinity. And that's because that critical point played the role of an inflection point. All right, folks? So, with that said, we now have methods for finding intervals of increasing and decreasing behavior for our functions using those critical points and the domain of the function. What we're going to come back to and look at next is continuing that idea of intervals of behavior for our function and going just a little further and talking about intervals of concavity. Since we're on the topic of intervals, let's continue the topic of intervals. And let's go over now and start to talk about topics of intervals of concavity. The derivative is still going to play a role. And this process of using test numbers and the like is still going to play a role. So we're going to see very similar behavior and procedure to what we've just seen previous. And we'll come back and look at that in our next video, folks. But yeah, we're going to come back and talk a little bit about intervals of concavity. And then when we have intervals of increasing and decreasing and intervals of concavity developed, where we're able to go with there is to talk about extreme values. What you're noticing is your extremes are happening at the ends of your intervals of increasing or decreasing behavior. And what we're also going to find out is that concavity is going to play a role or could play a role in helping you to determine where you have an extreme value. Because if you think about being concave down, at the top of that concavity, you're going to have an extreme maximum. So concavity is also going to help us a little bit with the extreme values. Another reason why we're going to look at it before talking extreme. All right. So we're coming back to those videos next time, folks. But with that said, I will end this one. And I'll see you in the next one.